Today we are going to look at a completely different topic, probabilistic methods. It's a way to show the existence of some good structure, and this is done using probability distribution or probability methods. This is why it is called probabilistic method. At this point, this sounds vague. What do I mean by good structure? This could be a mathematical structure, that could be a combinatorial structure. You can think of it as kind of a graph. So you want to show that a particular kind of graph exists or something, and this is what you want to show. Important thing is that the problem description will not have any mention of probability. Only the proof idea will require probability. It will be a surprise that we can use probability in such things to show the existence. Let me look at the idea. The main idea is that we define a probability distribution over a set of structures. So if you are looking for proving that a kind of nice graph exists, then we show a probability distribution over a set of graphs. Once we define it, then the task would be to show that there exists a good structure which is equivalent to showing that the probability of getting a good structure is non-zero. So clearly, if the probability of having a good structure is non-zero, that means there exists a good structure, and that will show the probability. At this point, it sounds very vague, so let's move to the examples that will make it very vague. We will take the first example from Ramsey theory, which is covered in graph theory. It might have been covered in your first course on mathematics of computer science. If not, let me remind you what it is. We are going to talk about undirected graphs. They are represented by vertices and edges which do not have direction. And let's say that the size of the graph is n. That means there are n vertices in my graph. Let me put it in a practical problem. You are given 6 people. I make an edge if A and B are friends. So between 6 people, I have a graph which represents friendship between them. The claim is either there are 3 people who are all friends, or 3 none of which are friends. You might want to think about this problem and you can prove it using case analysis. But let's model it in terms of graph theory. The 2 important concepts are independent set. So this is a set of vertices, more precisely subset of vertices, such that no 2 pairs are connected. That means for all I, j element of S, Ij is not an edge. The opposite concept is called a clique, where for all Ij element of S, Ij is an edge. None are friends, and this is saying all are friends. So the previous claim changes into any graph on 6 vertices has either an independent set or clique of size 3. Such things are called RK. More precisely, this is the least n such that any graph on n vertices. So remember the quantifiers. For all graphs on n vertices, there exists either a clique or independent set of size k. It will be illuminating to look at it as n increases. So if n is very, very small, if n is equal to 1, k, or so on, it is very, very easy to find a graph where none of this happens. There is no clique or independent set of size k. But as n increases, it becomes harder and harder to create such a graph. And if n is big enough, it seems intuitive that either there will be a clique or independent set of size. The exercise here proves that R3 is less than equal to 6. As an exercise, you can prove that there exists a graph on 5 vertices which does not have a 3 size independent set. So this exercise mixed with this will show that R3 is equal to 6. This is the least n such that all graphs have either a 3 size independent set or a 3 size clique. Our objective today is to prove that we can give a lower bound on Rk. How should we say that for this particular n, definitely there is a graph for which there is no monochromatic. Okay, so let me just make this notation to make it easy. Monochromatic means either an independent set or a clique. This is my new notation to make it simple. So I want to say that if n is equal to something that is going to the lower bound, then there exists a graph which has no monochromatic subgraph of size k. You can easily prove when n is equal to k, there is a graph which has no monochromatic subgraph of size k. But can we give a better lower bound? We will use probabilistic method. So what is the probability distribution? Our probability distribution is going to be over graphs, and it is going to be the simplest one. It's the uniform distribution over all possible graphs on n vertices. How many such graphs are there? 2 to the n choose 2. Other way to say it is equivalent way. We pick each edge independently and with probability half. Under such probability distribution, we want to show an existence of good graph. What is a good graph? Does not have k size monochromatic subgraph. So we have to find the probability of having a good graph. Instead, we will find the probability of a bad graph. So first, instead, find probability of one subgraph to be monochromatic. That you can easily show is 2 times 2 to the minus k choose 2. Now this is the number of edges in the k size subgraph. So for the entire subgraph to have all edges, this is the probability, and 2 appears because it can either be an independent set or a clique. The probability that one subgraph is monochromatic is this. Now using union bound, we can prove that no subgraph is monochromatic that is bounded by the total number of subgraphs of size k multiplied by the probability that that subgraph is monochromatic. So probabilistic method tells us that probability of good structure is greater than 0 if this probability, the probability of having a bad graph, is less than 1. This is equivalent to there exists a good graph. For all n, If this is satisfied, then n is a lower bound on Rk. You might want to just focus on this point once more and make sure that you understand this. This is the crux of probabilistic method. Since we were able to show that probability of a good graph is greater than 0, that means if n satisfies this constraint, then it's a lower bound on Rk. And this gives us such a thing is a lower bound. So as an exercise, we can prove that this satisfies this equation. So we got a non-trivial lower bound. K plus 1, all those we can prove, but here we have got a much bigger lower bound on the Ramsey number. So we have shown that Rk should be at least 2 to the k by 2. A small point here, the proof is called a non-constructive proof, in the sense that we did not give a graph which was good. We just showed existence. It seems that such proofs are not really useful for algorithmic purposes. We are not outputting a good graph. But this can be an algorithmic way if we are allowed to have some compromise. So if we say that n is equal to half to the k by 2, then probability that a good graph exists becomes very big. What does it say? It says that a random graph is, which gives us a randomized algorithm. And that randomized algorithm is very simple. We just pick a random graph, and with high probability it is going to be good. This analysis in general does not give us an algorithm, but if we compromise slightly, here we have a factor of half. Here we did not have a factor of half, so if we just decrease the n slightly, then we get a randomized algorithm. And the randomized algorithm is very simple. You just pick a random graph. And by the analysis, we know that it is good with high probability. It is not going to have a monochromatic case of graph. That means it is not going to have an independent set of size k or a clique of size k. The previous example of Ramsey numbers is interesting, but you can have a counting argument to show the lower bound.